Welcome back to this NPTEL online certification course of molecular rearrangement and reactive intermediates. In the previous class, we started learning about the organosilicon chemistry. We have learned about the organosilicon compounds, their discovery, their bondings with oxygens, with the halogens, and we talk about the the alpha effect of the beta effect, different type of reactions, and end up with the formation of the polymer from the silicon. In the today's class, my focus will be to start with the silicon based protecting group and then the reaction of vinyl and alkaline silicon compound with the electrophile. We are going to learn about again this alpha effect and beta effect in this class too. Okay, so let us start the today's class. Here we are going to talk about first the silyl protection of the corresponding alcohols and their deprotection. Again the acetal formation using trimethyl ethyl silyl triplet. Then there will be electrophilic substitution reaction of the different type of reaction of vinyl and alkyl silicon compounds in the hydrosilylation and the Peterson olefination. So in this particular part, we are going to learn about the protection of alcohol group using different silicon based reagent. Okay. So we are going to talk about the different type of protecting group. I think we have already heard about TMS chloride, correct? I think this is a very common reagent you guys have seen. It is a very reactive silicon compound. So if you have a alcohol here, you can react with the corresponding TMS chloride in place of a base to quench the HCl formed to form the OTMS. So this is called trimethyl silyl ether, but it is not only trimethyl silyl, but there are various different, like it could be a triethyl silyl, it could be a isopropyl dimethyl silyl. So there is isopropyl comes in, there is a 2-ethyl 1-isopropyl. Okay, there could be a tarbutyl with dimethyl, tarbutyl with diphenyl, and triisopropyl. Okay, there are so many different type of varieties, and you can see what is happening going from trimethyl to the tarbutyl dimethyl phenyl. We are seeing the steric hindrance around the silicon is getting increased. So again, if you have a very sterically hindered silicon, one of the problem going to happen, if you try to do some sort of a reaction where the nucleophile going to approach to silicon, that will be getting blocked once you have a very hindered group around the silicon. And not only that, so that is number one. The number two is, if you have a alcohol here, it is a secondary versus you have a primary. So this is a primary. So now if I have to selectively do a protection, then we can use a bulkier group which can be only going to protect the primary one over the secondary. Okay. So that we can be done using that. So that is the two advantage using this type of bulkier protecting group. Also they are very bulky, then at the same time, as I mentioned, the nucleophile cannot able to approach, they will be difficult to remove as well. So after you form the protection, means after you form this corresponding silicon ether, then the next thing is how do you deprotect them. There is two different deprotection, one is under acidic condition, another is under fluoride condition. So under acidic condition, if you have this silyl ether, once you treat with the H plus, this is going to bind with the oxygen, and now if you treat it, if there is a water can attack to the silicon, okay, that can able to break this bond to get your starting material back or get your compounds back. Okay. At the same time, if you treat with the F minus, then it is going to attack to the silicon. As I mentioned, first thing is formation of these pentavalent silicon compounds with trigonal bipyramidal structure. And now what is going to happen, there will be cleavage of this silicon oxygen bond to form this RO minus, which is going to take H plus to form the corresponding ROH. And because of this silicon fluoride bond is very strong bond, that is why you end up forming this compound. Okay. So these are the two different deprotection. Now we are going to learn that are they going to deprotect at the same time, or what is that their difference on the order of the protection versus deprotection. I think in terms of protection, as I mentioned, that if you have a primary versus secondary and you are using a bulky silyl ether protecting group, then always the primary will be protected faster than the secondary. That is number one. But now if you come to the deprotection order, then the TMS will be deprotecting very faster, the trimethyl So, this is the order, then triethyl tributyl, triisopropyl, and then you have this, the tributyl diphenylsilane. Okay. Very similarly, if you have a basic medium also, I think if you have this, if you using the corresponding the fluoride minus there, you are also going to, the TMS will be the one going to deprotect faster. Again you can see as the steric bulk is increasing in this direction, you are seeing that their stability is increasing. We can also able to compare their half life in the basic medium versus in the acidic medium. You can see in this direction you are getting the steric bulk is getting increased, and you can see at the same time once the steric bulk is getting increased, your stability is getting increased too. So, these tricks of the the stability in terms of acid and basic condition can help to do the protection first and then to conduct many different transformations. So, here you can see this phenol OH groups was getting protected using triisopropylsilane here. Okay, it is a TIPS chloride. So, first thing in this reaction you can see first there is alkylation of nitrogen with the aniline happening, and then there is a protection of this. Okay, then further what is going to happen, they are going to go for a N acylation to form this compound, and after several steps they are able to prepare this, and you can see in this 16 steps this OTI, the TIPS group is remain stable. Okay, so after they have done their synthesis, when they want to go close to their final product, now they can do the deprotection using TBAF, tarbutyl ammonium fluoride, which have a F minus source, which can able to now deprotect to form the corresponding phenol. Then I think in the total synthesis of Taxol, you can see there is a, TBDMS group here, there is a triethylsilane here, and in place of the HF pyridine at 0 degree Celsius, you can able to selectively deprotect this particular protein group, keeping the other remain protected. So, that is what is happening. You can see there is a difference in the size of the silicon protein group, and the steric environment can allow to deprotect selectively this secondary one compared to this one to form this as a the corresponding alcohol, which can be able to convert to the natural products. So, the other important thing, so these are can be used the TMS triplet, which also used in the laboratory very often. So, if you think about TMS triplet, then people also use them for this conversion, that if you want to go for a acetal from the corresponding aldehyde, if you want to form a acetal, you can also use TMS triplet. Of course, you can think about using PTSA or paratoluene sulfuric acid, or but again I think if you use those acid source, the one of the problem is if there is a trace of little bit of water there, then you will not able to get to the equilibrium towards this product, you might get back to the corresponding starting material. So, there will be a mixture and it will be difficult to control, but TMS triplet can be used, it can do the job. So, here what is happening, the oxygen lone pair is attacking first to the silicon to get rid of this triplet, and then what is happening, then the methanol is attacking here to this corresponding carbon here, forming this compound. Again you have the oxygen lone pair, so it is going to react with another TMS triplet to form this compound, and now you can see your oxygen is bind with 2 TMS group. For this oxygen lone pair can come back and get rid of this. Okay. Now once you have this corresponding oxonium, now the methanol can now easily attack here to form this corresponding acetal. Now silicon can be used as a protection group for the alkyne. Suppose you have a alkyne here, and now if you think about, if you try to compare the acidity of different proton, so which proton will be the more acidic? I think if you have know about the pK, you will be agree with me that this is the hydrogen which is attached with the sp. So, you can see this is the sp carbon versus this is the sp3. If you remember in the carbon ion stability, I think I talked about at the beginning when I talk about the carbon ion, at the time if you remember, the anion in the sp carbon will be more stable because of I think it can pull the electron density towards the nucleus. So, this proton will be more acidic, but if I want to do functionalization here, suppose I want to do a functionalization here in this particular carbon, for how do I do that? For that we can use a tricks, we can do a silicon protection and a deprotection strategy. That means first thing is we know that we can able to abstract this proton very easily using RLI. We have learned about that, pK around 25. If you use a butyl lithium, this proton can be abstracted, and then if you use a corresponding, it can form the corresponding lithium, and then if you treat corresponding TMS chloride, it will form this protected alkyne. Now this proton is gone. So if you treat a n-butyl lithium, this can able to comfortably able to lithiate this proton, able to generate the carbon ion at that carbon, and now you can do some, you can treat with the electrophile, you get your corresponding product, and now you just use TBAP for the deprotection. TBAP can react with the silicon, attack on the silicon, and get rid of from this corresponding alkyne to get to the corresponding product. So here silicon job is just masking the alkyne, and then at the end it is going to demask to get to the corresponding product. The other important fact is, if you try to compare, in general, if you see a normal alkyne versus a silicon alkyne. So if you have a carbon versus a silicon, these are the corresponding silicon analog is much more reactive. That means this alkynyl silane will be much more reactive compared to alkyne towards electrophile. Why it is that? Because of the stability which is forming in the corresponding tangent state, because of the beta effect of silicon. That means once this electrophile will take the electron density from the alkyne, it is going to form the corresponding carbocation, correct? So now this carbocation is going to form in the beta position here compared to this one, okay. It is not in the alpha position, because this will be not going to get stabilized. This is the one which is going to get stabilized when it is going to form at the beta position, because if it is the carbocation is going to form at the beta position, then the carbon silicon sigma bond electron density can be given to that to the empty orbital, because so there is this field carbon silicon sigma bond can be, sigma electron density can be given to the vacant p orbital to stabilize this corresponding carbocation. Okay. Again, I think this alignment is very important, so that the electron density can be given, so that can stabilize. Now what is going to happen if this is giving electron density? I think I mentioned clearly, if this is giving electron density here, now a nucleophile can easily come, because now the carbon silicon bond is becoming weak, because the sigma bond is already giving electron density to stabilize the carbocation. So a weak nucleophile can come and attack to the silicon and cleave this bond to generate the alkyne again. That is why what is happening from the starting to the product, if you start with the silicon, you are replacing silicon by your electrophile in the product. Again, there could be several different electrophile. We are showing here first with AlCl3 and acetyl chloride. Okay, it can able to introduce the COCH3 groups in the place of silicon. So your silicon is gone and you introduce CH3CO group. Very similar mechanism here. I think you know about that. That once you have this CH3COCl, I think I already shown you that once you have the AlCl3 as a Lewis acid, it can form this species here. Okay, so now you can see, now once this is forms, the alkyne can react with that, and now there is a formation of this plus in the, so there is a beta position. Due to the beta effect, it will be stabilized, which finally the Cl minus can comes in, attack here, cleave this bond, because the bond getting weak to get to the corresponding product. We have learned about reaction with the alkyne, but now we are going to learn that if you have vinyl silicon compound here, or the vinyl silane, then if you have a E versus Z isomer, if you treat with the corresponding electrophile, from E isomer you will get to the corresponding E product. That means again the silicon will be replaced by the corresponding electrophile here. So there will be no change from E to E, you will get E. So that will be very, you see the reactions are going to be very stereospecific, and from Z you are going to end up getting to the Z isomer as well. Okay. So again, what is happening here, once the E vinyl silane react with the corresponding electrophile, it can generate a carbocation, which is again, if you see, this is alpha, this is beta, and to give electron density they have to be in the anti-periplanar orientation, that the silicon sigma bond electron density can be given to the empty orbital in the carbocation, empty p orbital, and finally because of the electron donation this carbon silicon bond becoming weak. So, Cl minus can be able to cleave it to form this corresponding vinyl product. If you start with the Z vinyl silane, that can also react with the electrophile, generate the carbocation, again it can rotate, this bond between this carbon carbon bond can rotate. So, that rotation continues to get to the place where it can able to give electron density to the empty p orbital, and finally the chloride minus can attack to the silicon to get to the corresponding product. So, starting from E you are getting E, and from Z you are ending up getting to the Z isomer. Here some of the example here using ICl as electrophile, you can introduce a iodine here. Okay. Again I think as I said the mechanistically very similar mechanism happen, and once you have this compound it can be converted to a very important anti-cancer drug called tamoxifen. Again the mechanism is given here. If you have a TMS, then first the iodinium formation is going to happen, and then you can see this can able to keep the iodinium, there will be in the decomposition of iodinium going to form this corresponding carbocation which is again in the beta position, and finally the Cl minus can attack to the silicon going to form a double bond here, okay, to get to the corresponding product. So, you can use a Lewis acid, and it could be a intramolecular reaction where the vinyl silane can react intramolecularly to acyl chloride. I think I talk about reaction of acyl chloride with AlCl if you remember in case of alkynyl silane. Here very similarly in case of titanium tetrachloride this very similar thing going to happen once you have a Lewis acid, and that can go for intramolecular attack. So, that intramolecular attack going to take place. So, this can able to form first this type of species here, the Cl will go form this species which is going to get attacked from the silicon to generate. So, if you think about this going to go for attacking here, and you have a corresponding silicon here, and you will be forming a carbocation here. Okay. And now what is going to happen, the Cl minus going to come back, because this bond is giving electron density, this bond is giving electron density to the corresponding carbocations, the sigma bond, that is why this bond will be weaker to form the corresponding product. So, we have learned about the reaction of alkynyl silane and then the vinyl silane. Now, we are going to learn about the aryl silane. If you have aryl silane, you try to treat the electrophile. What is going to happen? You end up getting several different products I have mentioned here. There are several different possibility, correct, but what is going to happen, the major product will be formed through the corresponding ipso substitution. So, we end up getting to this product, the ipso substitution product as a major product. So, what is happening here? Again you can think about that if you go for a ortho attack here, then you are generating a carbocation which is alpha to the silicon. Again we know that silicon stabilizes carbon 9 in the alpha position, not the carbocation, because so that is why this carbocation will be highly unstable. If you go for a para attack, then you are generating a carbocation here which is not even alpha, not even beta, it is okay, or it is a gamma carbocation. So, it is not stable. But if you go for a ipso attack, you generate a carbocation which is beta. Now, again if you have a beta carbocation, what is happening here? It can able to, so orbitals are perfectly aligned here. You can see we have already discussed this in the previous case also, that once the orbitals are aligned like that you have a carbocation here and you have this silicon sigma bond, then this can give electron density to that corresponding carbocation, which is happening here. Orbitals are perfectly aligned for stabilizing this corresponding tangent state, which can now the nucleophile can attack here to get to the corresponding product. Okay. And then if you think about, there is another possibility that what about if you have a meta attack, then carbocation is forming to the beta position. You might argue that sir, here also carbocation is forming beta position, why it is not going through this route? The problem is that here the silicon carbon bond is orthogonal in terms of the these sigma bonds, sorry, this empty p orbitals of the carbocation. So if they are, if they are orthogonal, then they cannot able to give electron density. The sigma bond cannot able to give electron density to the p orbital of the carbocation. So that's why this is not possible. That's why only this ipso substitution which is favorable because of the this corresponding the stabilization of this positive charge which is the in the beta position to the silicon. Then I'm going to talk about some of the chemistry of the TMS CH2I compound. So this is an important compound here because people can able to convert this iodo to the corresponding Gigner, because you can see you are literally generating some sort of a, you can compare this species of some sort of a carbon ion here. So you have a carbon and some sort of anion here, you can think about like that. Okay. So if you can see once you are making a Gigner means you are making some sort of a C minus and M plus. So this is the alpha position of the silicon, and alpha position of the silicon is always silicon stabilize the corresponding carbon ion. That's why these compounds can be synthesized and can be used, can be react with corresponding esters here, and after the 2 equivalent of the silicon 2 equivalent of the Gigner can attack here if you remember. Then after that Peterson olefination can happen between these two groups, there will formation of the olefin. Okay. So the oxygen silicon bond formation happen, and then there is a once that is going to happen, this will allow formation of this corresponding double bond. It can also act as a Wittig reagent. So you can take this, you treat with that corresponding CH2 minus PP, the phosphorus based ylides. Finally, if you treat with the butyl lithium, it will able to form the corresponding Wittig ylides, which can react with the corresponding carbonyl group to form this corresponding allyl silicon compound. So you can able to synthesize allyl silicon compound starting from this particular compound here, or you can start with again from, so you can use two different technique from using this Me3SiCH2I, either you can use the Gigner technique or you can use this Wittig reagent to get to the corresponding allyl silicon. Of course, there are more method, there are several other cross coupling strategy also you can use for this, and also there are some hydrosilylation strategy. So I think now we have learned about the synthesis of the allyl silicon. We are going to talk about some of the reactivity. Okay. So one of the important thing is, as I said before also, that once you have this allyl silicon, the interaction between this parallel carbon silicon sigma bond and the p orbital of the pi bond. So this interaction is possible here. This sigma bond can interact with these pi bonds, but here once you have a vinyl, that is not possible. So now if you have a electrophile, as I mentioned, that can this olefin electron density can be given to the electrophile to generate this beta silyl carbocation. Because now because of the sigma bond is giving electron density here to stabilize this beta silyl carbocation. So this silicon bond, carbon silicon bond is weak, so X minus can attack here to form this olefin here. So finally what is happening, the overall process is electrophilic substitution with a allylic rearrangement, you can think about. In general, if you try to think about a allyl silicon, we generally write this way, that if you have a electrophile, we generally write this way, that it can able to trap electrophile and form this sort of a product. But in general, if you, I think you can think about this is the mechanism what it is happening to form this product. Okay. So it is going through some sort of mechanism like that, where it is forming this some sort of a beta silyl carbocation. Again, if you have this compound, you can able to treat with Lewis acid. If you have titanium tetrachloride Lewis acid, you can treat the alkyl halide to introduce this R group here. You can take a acyl chloride to introduce the COCH3 group here. Acetyl group can be introduced. It can go for a 1,4 addition in case of titanium tetrachloride. It can also open up epoxide. So if you have a Lewis acid, and then this corresponding allyl silicon can attack to the epoxide here to open up the epoxide to get to this corresponding product. Okay. So again, I think the very similar thing we are saying, that if you have a Lewis acid, what is happening? It is forming this reactive oxonium ion. Once it is forming this oxonium ion, then now this double bond electron density can be given here, forming this you are forming this the carbocation in the beta position. Now this X minus can attack on the silicon to get to the corresponding product. Here you can see, I think the mechanism is given here, but you can use the TMS triplet here to form this corresponding silyl acetal, okay, to get to this corresponding oxonium ion, or you can use the corresponding ROH and H plus. Either way you can able to generate this corresponding oxonium ion, which can able to react with the allyl silane to form this corresponding homoallyl ethers. Okay. So, this is the way you can able to form the corresponding homoallyl ether. So, this is a problem given here. If you want to go for intramolecular cyclization, because now you have to use a Lewis acid which can activate this on the OME. So, once it will be activated, it can able to form some sort of a intermediate like that. Once you have a Lewis acid, then it can this can come back and get rid of this, okay, forming this oxygen plus, which can now allow this cyclization to happen to form this compound. So, here what is happening at the end, you are generating a homoallylic ether. Okay. The hydrosilylation reaction, it was in 1947, it was discovered by F.C. Whitmore, and the co-worker actually discovered the hydrosilylation reaction of 1-octene. Here it is happening. So, in this hydrosilylation reaction, 1-octene react with the trichlorosilane in the presence of diacetyl peroxide. So, in place of diacetyl peroxide, what is happening? The silicon SiCl3 and this H is adding in the two different part of this olefin, and what you are seeing very similar to the hydroboration, we are also seeing the anti-Markovnikov selectivity here. Again, what is happening in this reaction? First thing, I think this reaction is going through some sort of a radical pathway. Okay, you can see because of this, you have this type of the peroxide linkage here, which is going to get cleaved in place of heating to generate CH3CO dot. After the CO2 getting eliminated, it can form CH3 radical, which can able to form this corresponding silicon radical here. Now, silicon radical can add to the olefin. Okay, it is going to form the beta radical in the silicon. If you remember that silicon can stabilize radical in the beta position, which can now go for a hydrogen atom abstraction to get to the corresponding product. Again, I think this chemistry was developed for last 4 and 5 decades. There are several different methods was developed for hydrosilylation reaction. They are from olefin to alkyne to carbonyl to imine, cyanide, every single different compounds you can able to introduce the silicon and hydrogens. So, this method can be done in presence of transition metal or in the absence of transition metals. So, now I am going to talk about another very important topic, which is the last part of the today's talk, is the Peterson olefination. So, here you are going to see that this is, I think we have learned in the previous part that once you have this, you are generating a carbanion alpha to the silicon. Okay, so, now this can able to react with the corresponding aldehyde to form this beta silyl alkoxide. Once you have this beta silyl alkoxide, under basic condition it can undergoes a corresponding stereospecific syn elimination, and in presence of acidic condition it is going to participate in a stereospecific anti elimination. Okay. So, now if you can see here, depending on this syn and anti elimination, you can end up getting a stereoselective formation of the olefins. Okay. We are going to explain in the details how this olefin formation is happening. It was discovered by Professor Donald John Peterson. So, first once you have this anion here alpha to the silicon, it can act to the corresponding aldehyde, form the beta hydroxysilane, and now you can see that once you treat with a, so now there is two different cases. If you have a acid versus a base, in case of acid, what is happening, your OH can be getting protonated. So, it can form the H2O plus here. Now, you can see there is anti elimination is happening, because this silicon can give electron density to the corresponding sigma star here. The sigma to the sigma star electron density can, donation can be happening. Now, because of this the silicon bond is weak. So, this bond can be cleaved to form corresponding cis olefin. But once you have treated with the corresponding base, now there will be a syn elimination happening. This O minus can be attacking the silicon, forming this sort of a carbon ion here, or can be a oxa silicate intermediate. Either way, what is going to happen, it is going to get rid of the silicon, going to form corresponding trans olefin. Okay. So, I think you understood how this two mechanism is operating to giving you the cis. So, anti elimination going to give you the corresponding cis product, and C in elimination going to give you the corresponding trans product. Here you can see again, I think it is starting from this Me3SiCH2 already, you can able to generate this anion, and now you can able to react to this carbonyl compound to form this corresponding olefin. Okay. With again you can see the Z selectivity is very high, you can end up getting to the corresponding Z product, and which can be converted to the natural products here. Again another example here, you can treat LDA here, you need excess LDA because you have acidic proton here to get to these corresponding compounds. Then you can treat with the corresponding carbonyl group here to get to the olefin here. So that they are although you have carboxylic group is unprotected, but that does not make any problem here, because once you have this carbonyl next to the silicon, it is going to add to the corresponding carbonyl group, and then after the elimination it will form the corresponding product. So, in this part I think I talk about couple of important things about the silicon. You have learned about at the end the Peterson olefination, how you can able to get to the corresponding E versus Z, and then in the previous part I think the most important thing I am going to talk about, I think I have talked about is the protecting group for alcohol, different silyl ether protecting groups, how that is important, that if you want to protect primary versus secondary. And then also I talk about that if you have a vinyl silane or alkaline silane, if you treat with the electrophile, it is just replace the silicon with the electrophile. So, if you start with the E, the vinyl silane, you will end up getting the E product, starting from Z you end up getting to the Z product. Again these are the references, and again thank you so much for coming to the class. I am going to see you guys in the next class. Thank you.